Hi, this is Alex from devstories.eu. Python, Cheminformatics, and AI, episode 16 of 22. To teach an AI how to invent a new molecule, you first have to teach it how to completely destroy one. It seems entirely backward, but this systematic destruction is the exact mechanism used to generate novel drugs from scratch. This is the core intuition of denoising diffusion probabilistic models. Traditional molecular design is incredibly labor-intensive. If you want to automate the discovery of novel compounds, you need a model capable of exploring a vast chemical space without generating invalid nonsense. Early deep generative models tried to map this space directly. Denoising diffusion probabilistic models, or DDPMs, take a different route. They treat molecular generation as a progressive denoising problem. The framework is split into two distinct Markov chains, the forward process and the reverse process. The forward process is strictly about data degradation. You take a valid, known drug from your training set. Over a fixed sequence of steps, you progressively blur its atomic coordinates by injecting pure Gaussian noise. The amount of noise added at each step is controlled by a set hyperparameter schedule. At step 1, you perturb the atom slightly. The molecule is a bit distorted but still clearly recognizable. By step 50, the structure is severely warped. By the final step, typically denoted as step T, the original molecule is entirely gone. You are left with a random cloud of unstructured Gaussian noise. This forward process does not require a neural network. It is a strict mathematical corruption. It serves a vital purpose because it generates the ground truth for our training data. Here's the key insight. Because we controlled the exact amount of noise added at every single step, we have a perfect step-by-step record of how the molecule fell apart. The reverse process is where the neural network comes in. The model is trained to walk that exact path backward. We feed the network a corrupted molecule at a specific time step. We then ask it to predict the specific noise that was added to reach that state. We evaluate the model by comparing its noise prediction against the actual noise we injected during the forward phase. We update the model parameters to minimize that difference. Over time, the network learns to denoise the data step by step, gradually restoring the original data distribution. To generate a completely new molecule, you execute this reverse process from scratch. First, you sample a completely random cloud of Gaussian noise. Then you pass that noise into your trained neural network, along with the starting step number. The network evaluates the input, predicts the structural correction needed, and returns a slightly less noisy cloud of atoms. You loop this subtraction process. You pass the new output back into the network for the next step down. With each iteration, the random cloud tightens. The model continuously strips away the noise. As you step backward towards step 0, atomic coordinates snap into place, and a valid chemical structure emerges. You pull a completely novel molecule out of the initial static. The model does not just memorize a database of existing drugs, it simply learns the universal process of removing chaos to leave behind stable chemistry. If you would like to support the show, you can search for DevStories EU on Patreon. Thanks for listening and keep building.